So let's talk about theoretical approximations, okay? It's a very tough name for something that you already know, so I'm just going to show you that you already understand what that is. We know that there are two types of sampling distributions. There's the derived and the ideal sampling distribution, right? So let's work on this population of Dutch people, and let's, okay, for just a second, we're going to take this divine look of the world in which we know all the values, and in that divine look, we know that the average in the population is 179. But other than that, we don't know what the population distribution is, and that's why we're trying to conduct a study to find out what the average of the population is. And we have infinite money, okay? So if we have infinite money and we're trying to estimate the population value, let's take the first sample, 300 dudes, take their average height, 180. Stop here. No, we're rich, so let's keep going. Let's take a second sample, average height, 178. Let's take a third sample, average height, 170. Let's keep doing that until we have 25 samples, and then we can plot those samples into an ideal sampling distribution. So we know that we found 175, 179, 1, 2, 3, 4, 5 times, 5 samples out of the 25, right? That's our point estimate. That's our expected value if we were to draw a new sample. Great, we all know that stuff, and this is an ideal sampling distribution because we have infinite money, right? Because being rich is great. And the reason why it's great is because our population value is going to be exactly the same as our ideal sampling distribution. Sometimes a little too high, sometimes a little too low, right? Our samples, like the samples that we're drawing, sometimes they're too high, sometimes they're too low. But on average, they're pretty accurate, right? The average of all samples is going to give us a pretty accurate estimate of the population, which is 179. Great. But we ain't rich, right? And we need to be funded by the state, or by a very greedy corporate boss. So we're not going to be running 25 surveys with 300 people in each of them. That would have been 7,500 people, 7,000 euros to, run. Very expensive. Now, that's why we take one sample, okay? And that's all we got. And it's a sample number one. And let's say we got average height 180, which is not exactly the height in the population. And then we take that average 180 and we plug it in the middle of a derived sampling distribution of value 180, right? Well, being rich was way better. But actually, look, at least it's one survey with 300 people, 300 participants. This is 285 euros. It's actually pretty cheap. And it's giving us like a pretty solid result, It's like a Mr. Beast. I tried 25, running 25 samples versus one. Look at the difference. Like researchers choose the bottom one because it's actually pretty solid. But hold up. How do we get these distributions? You might be asking yourself. And that's what the chapter is talking about. Well, look, this ideal sampling distribution, we got it by plugging in all the numbers and drawing a bell shape on top of it, right? So that was pretty easy. Here in our ideal sampling distribution, we first placed the data points of the averages that we found in our samples. Then we saw it looked like a bell shape, and we're like, oh, interesting. Then we placed this bell shape on top of these numbers, okay? But it's not exactly matching yet. So we're going to stretch this bell shape in and out until it fits perfectly, right? So this is what we do. We stretch that. And once we stretch, it's a perfect fit. And we're happy. But here, like on a derived sampling distribution, what we did is we placed the data point. And now what? What do we do? Well, okay, here's the thing that they're using. In the book, they're saying that this data point is in principle representative of the population. So we call it in principle representative. Okay, it's the short. In principle, this data point is representative of the population. 180, 179, which is the population value, it's pretty representative, right? Now, after that, SPSS is going to give us a standard error based on the sample size of our sample our single sample that we gathered. So I want you to picture it this way, like SPSS has a bunch of bell-shaped drawings in their backlog, and depending on the number of participants you have, it's going to give you a different shape. Okay, so here are the 3 shapes, different shapes for different participants. You can see, this is something we're going to talk later, that the more people we have in your sample, the narrower your distribution, okay? The more precise your distribution, which is interesting. But let's say we had 300 people in our sample, so this is the appropriate distribution shape that we can get. And we get that, and SPSS knows that the standard error for 300 people is going to be 1. okay? It's doing all the calculations for you, so you don't have to worry about that. So for 300 people, usually it's 1 centimeter, right? And if we're talking about height. So SPSS is going to know that. It's going to make that inference using some formula based on the sample size, okay? And then knowing that the standard error is 1, we're going to place that distribution there, and we're going to stretch it until one z-score matches the standard error. So what's one z-score? Z-score is the distance between the middle bar and the first bar away from the middle, away from the average. So we're stretching this, right? In and out, and then we finally found this distance, right, of 180 to 181. That's a 1 centimeter distance, and that's also the standard error. This process is what we call theoretical approximation, okay? Because we're using theory, we're using this formula that SPSS is calculating for us to approximate the shape of our sampling distribution that would have been the shape of an ideal sampling distribution, referring to a population distribution, okay? So we're trying to sort of create in a laboratory, right? We're trying to create a synthetic ideal sampling distribution, and that's what the derived sampling distribution is.